In our previous video, we learned that according to Arrhenius, according to the Bronsted-Lowry concept, acid is any molecule that is capable of donating a proton, while a base is a substance that will accept the H plus sign. So H plus sign donor is an acid and H plus sign acceptor is a base. So we have taken some examples in the last video. Now we'll discuss here some of the acid-base pairs. So suppose we have the hydrochloric acid HCl. When the hydrochloric acid will behave as an acid, so then means when it will release a proton, when this hydrogen will be released, so when one of the hydrogen is lost, so you get a Cl negative. Here this hydrochloric acid donates a proton, so therefore this is an acid, and Cl negative will be its conjugate base. And we also learned in the last lesson that the strength of an acid actually here, how strong this acid is, it depends on the stability of its conjugate base. If the conjugate base is stable, then the acid is more stronger. So let's take some more examples of the acids and their conjugate bases. So you can here call this one as an acid-base conjugate pair. This is hydrochloric acid and the Cl negative is its conjugate base. So this is a conjugate acid-base pair. Similarly, we can take the example of a nitric acid HNO3. HNO3, when it releases a proton, means when it acts as an acid, so you remove one hydrogen there, you get a NO3 negative. So NO3 negative is a conjugate base, right? So this is a conjugate base of the acid nitric acid, correct? So another example we can take here is the let's take the H2SO4, okay, the sulfuric acid. The sulfuric acid, when it releases a one proton, behaves like an acid, so it will be now having a HSO3 negative. So you can say HSO3 negative here, this is a conjugate base of the H2SO4, correct? And HSO4 negative can release a one more proton there. You can release a one more proton over here, minus one more H positive ion, so you get a SO4 negative here. SO4 negative. So SO4 negative now will be called as a conjugate base of the HSO3 negative. Now in this case here, so in this particular example, when HSO4 negative releases a one more proton, that means now this HSO4 negative behaves like an acid, correct? It behaves like an acid, and SO4 2 negative actually here, 2 negative will be now called it as conjugate base. Okay, so you can say the HSO4 negative acts like a acid here because it donates a one more proton, so therefore it's an acid. So HSO4 negative basically is an amphoteric substance. The amphoteric substances are those substances that are that can act both as an acid as well as a base. Means they can either accept a proton or they can release a proton. So suppose HSO4 negative, when it acts as a base, means if it accepts a proton, so you add a one hydrogen there, HSO4 negative, when it accepts a proton, it forms the H2SO4. So therefore now it will be like a base. So that's why this is a conjugate base, right? So HSO4 negative, we can say, is an amphoteric substance, right? It's an amphoteric substance. And we can take one more example here of the hydrogen cyanide. Let's take the HCN. HCN, we have a hydrogen carbon single bond there, and when it releases a proton, behaves like an acid, so release a proton, so you are left with a Cn negative cyanide here. Nitrogen has a lone pair of electrons also. So you can say cyanide here is a conjugate base of the HCN. Okay. So similarly we can see H2S. H2S again, it can release a one more proton, so forms the HS negative. So HS negative here is a conjugate base of the H2S. The water molecule can again similarly here release a one more proton and behave an acid, So its conjugate base will be hydroxide ion. So conjugate base of the water is hydroxide ion. Similarly, we can take some more examples of the conjugate acids and the bases. So let's take here an example of an ammonia here. Okay, ammonia, it can accept a proton because it has a lone pair of electrons. If you add one more proton, means now it behaves like a base, because if it accepts a H plus ion, so then you get a NH4 positive. So you can say NH4 positive is a conjugate acid of the ammonia. The water molecule again has lone pair of electrons, and it can accept a proton, means it can behave like a base. Okay, so it can form the H3O positive. Okay, so we can say H3O positive is the conjugate acid. Okay, this is the conjugate acid of the water. So now let's take certain acidic character of some of the molecules here. Let's see how this acidic character will change. If you have the if you take the example of the second period, right, the elements of the second period, in the periodic table, you see those elements in the second period. We have there the carbon, nitrogen, oxygen. So we have a carbon, nitrogen, we have an oxygen, we have a fluorine. So if you, let's suppose, take the hydrides of these second period elements. So from the carbon we can say it is the methane, CH4, nitrogen will be NH3 here, and from the oxygen it will be the H2O, and fluorine will be the HF. Now when these molecules act as acids, okay, when all these molecules, suppose if they act as acid, like HF, when it releases a proton, right, means it accepts, it acts as like an acid, so minus H positive. So now its conjugate base, the conjugate base of the HF will be F negative, correct? Similarly, when water molecule will act like an acid, means it will also release a proton, so you get a hydroxyl ion, right, OH negative ion there. And we have an ammonia molecule, suppose if it also acts like an acid and releases one more proton, so its conjugate base will be the NH2 negative here, right? Okay, and methane molecule CH4, again when it releases a proton, acts as an acid, so its conjugate base will be the CH3 negative. And as we discussed previously, that the strength of an acid actually depends on the stability of its conjugate base, and we know that the stability of those conjugate bases follows in this order. F negative is more stable than hydroxide ion, which is more stable than the NH2 negative, which is more stable than the CH3 negative, because fluorine is very much electronegative atom, more electronegative atom, so it can accept, it can bear this one extra negative charge. Oxygen is little less electronegative than the fluorine, and ammonia is less, and carbon is very, very less. So that's why the stability of these conjugate bases, right, all of these are what? These are the conjugate bases, okay, conjugate bases of the corresponding acids. We know that this this is the most stable here, right, this is the most stable one here, and this is the least stable one, correct, least stable one. So therefore the acidic strength, acidic order will also be in the same manner, right, means HF will be more acidic than water, than ammonia, than the CH4, because as I said, the strength of an acid or a base depends on the stability of its conjugate base. Here in this example, it is F negative which is most stable among these examples, and then the hydroxide, okay, OH negative, then NH2 negative, then the CH3 negative. So that's why HF is the most acidic molecule among these compounds here. Hope you got it. Thanks for watching the video. Bye for now.